So welcome to my channel on technology space with machine learning and artificial intelligence. So the today's topic is what is ship pivot point. This is a part one of a three-part series, and this is also part of the maritime technology playlist. So let's move on to the main content of this presentation. So let's try to illustrate why this is an important concept in ship navigation. In this channel, we have discussed that ship controllability can be a challenge when you are dealing with underactuated vessels in ocean-going conditions. So to overcome some of these challenges, these human navigators often use this concept of pivot point. In a way, that concept can be used to predict vessel position and orientation within a shorter time period. That means pretty much you are looking into the possible vessel motions. So that way the navigator will have some idea about what will happen to this vessel within that specific time period. You don't see many studies done in this area to explain this pivot point in a more scientific way and utilizing that pivot point into a more practical ship navigation conditions. So here we are trying to explain this pivot point in a more scientific content, and then hopefully that information can be utilized towards the future research. So let's move on to the main content of this presentation. So let's try to answer this main question of what is ship pivot point. I think it's not that the answer may not be a straightforward one. You may have to develop some type of a mathematical concepts to explain ship pivot point. So let's take one step backwards. I think even before that we have to explain the pivot point in a rigid body motion, which is going in a circular path. If we take another step backwards, we would go towards the point mass motion in a circular path. Let's try to explain that first and then come back to the rigid body motions as well as the ship motions to explain this concept of pivot point. So let's talk about a point mass in a planar motion. You can imagine this situation as a point mass moving in a frictionless table. Because of that reason, the gravitational field is going towards the surface. So the point mass is denoted by m. And then the center of gravity in this point mass is denoted by Cg. And this the motion in this point mass is somehow we have to relate to a specific point. So that point is denoted as this center of planar motion, which is represented by PC. So if we draw a vector from that center of planar motions to the point mass, that vector can be denoted by R in this figure. That's also named by trajectory displacement vector. So since this point mass is moving along this surface, it would have a velocity component. Here I am representing the translational velocity component in this case by capital V. So let's try to derive the kinematic equations for the translational motion of this point mass. In these situations, I am considering this point mass is having infinitesimal linear displacement of dr within a time period of dt. So because of that linear displacement, the initial displacement vector r has been changed to r plus dr in this figure. So the velocity in this point mass can be defined as this change in the linear displacement divided by the respective time interval. So this linear displacement can be represented by the final displacement vector, which is r plus dr, minus the initial displacement vector, which is r, and then that whole thing divided by the time interval, which is dt. Then you end up with the equation when r to r cancelled, you end up with the dr over dt equal to v, which is v is represented by the velocity vector in this point mass. And you should also note that the displacement vector r and the velocity vector v are perpendicular to each other. So let's try to derive additional kinematic equation for the translational motion of this point mass. In these situations, I am considering a infinitesimal velocity change of this point mass by dv. Therefore, the initial velocity vector v has been changed to the new velocity vector v plus dv. And in the same time, I am representing the translational acceleration of an, which is pointing towards the center of the planar motion in this point mass. So let's try to derive an equation for this translational acceleration. So the acceleration generally can be defined as the change in the velocity in this point mass. So the velocity change in this point mass within that time period of dt can be written as the final velocity of v plus dv minus the initial velocity of v divided by the dt. So then you end up with the equation dv over dt, which sounds like the time derivative of the velocity, which is also equal the second time derivative of the displacement and equal to the translational acceleration, which is denoted by an. You should note that the velocity vector v and the translational acceleration vector an are perpendicular each other. Therefore, the translational acceleration vector an and the displacement vector r are parallel to each other. So since we have completed the kinematic equations for translational motion of the point mass, let's try to do the kinematic equations for rotational motion of this same point mass. Here I am also assuming this point mass is rotating around this center of planar motion. And this situation we are considering it is having infinitesimal linear angle change of d theta within the time period of dt, and this d theta rotational angle also noted in this figure. So the angular or the rotational velocity of this point mass with respect to the center of planar motion is denoted by omega, and then the angular acceleration for this point mass is denoted by a omega. So the kinematic equation for rotational motion of the point mass is presented in this slide. So the angular or the rotational velocity of this point mass, which is denoted by omega, can be written as d theta divided by dt. And then the angular acceleration of this point mass can be written as a omega equal to d omega divided by dt, or the time derivative of the angular velocity. So let's try to combine this translational and rotational motion of the point mass into a single kinematic equation. So in this situation, I am considering this infinitesimal angle change, which is d theta, is equal to this infinitesimal displacement change dr divided by r. So this is how the angles in radians been calculated. So therefore you should remember this angle d theta is represented in radians. So from that you can end up with the equation saying dr equal to r times d theta. So let's try to get the time derivative of this equation. So the time derivative of this equation will be something like this: dr over dt equal r times d theta over dt. So as you know from your previous equations, dr over dt, which is equal to the translational velocity of the point mass, and then d theta over dt is equal to the rotational velocity of the point mass. So if you apply those values into the existing equation, you end up with the final equation, which is saying v equal to r times omega. So what that means, the translational velocity of this point mass is equal to r, which is the magnitude of this displacement vector, times the omega, which is the rotational velocity of this point mass. So let's expand our imagination by assuming that the point mass under planar motions is going through a perfect circle. So now this point mass is making a circular maneuver or circular motion. So there are some important features we should highlight in this situation. So the first feature is this centripetal force. So that means when this point mass is going through a circle, there would be a force which is acting on this point mass but pointing towards the center of the planar motion be there. So that is the force actually holding this point mass while it is rotating through a circular path. So that force is denoted by Fn, and the name is called as the centripetal force. So you know, if a force being applied to a point mass or a rigid body, what would be the next step? There would be acceleration in that point mass or the rigid body in the same direction of that force. So due to this centripetal force, there would be an acceleration acting on this point mass, which is denoted as An, and we call that as an normal acceleration, and this is a part of this translational acceleration in this point mass. So one important thing about tangential acceleration component in this point mass should be it is equal to 0. Because there's no acceleration going towards this velocity vector, it can circulate around a perfect circle. If there is acceleration component into this which is parallel to this velocity vector, you obviously know the velocity in this point mass will change. So that because of that reason, this point mass will deviate from this circular motion. So there's another important concept, since this tangential acceleration component, which is denoted by AT, is equal to 0. Due to the same reason, the rotational acceleration component, which is denoted by A omega, is also equal to 0. So let's try to derive some additional kinematic equation for this planar motion of the point mass. And this is a special case where this point mass is going through a circle. So the first equation would be about the normal acceleration component, which is denoted by An. So in this equation, it shows that An equal the time derivative of the velocity, which is denoted by dv over dt. So if you use the chain rule, you can actually divide that dv over dt into two sectors. Here it is represented as a dv over dr times dr over dt. This is where you can use the chain rules to expand that expression. Since this point mass is going through a perfect circle, dv over dr ratio is also equal to v over r, which is equal to a constant. So that can be replaced by v over r, and then dr over dt, you know that the time derivative of this displacement vector, which is denoted by the velocity of this point mass. So if you apply these two equations into the previous equation, you would end up with the final equation saying An, which is this normal acceleration component, equal v over r times v. So eventually that means v squared over r. So that means this normal acceleration component in this point mass, which is pointing towards the center of this circle, is equal to its velocity squared divided by the radius of this circle. So this is an important equation to remember when a particle moving through a circular motion. And then, since we already familiar with the normal acceleration component, which is pointing towards the center, we can also calculate the centripetal force, which is parallel to this acceleration. So here we are using the Newton's law, which is F equal to ma. So if you apply that rule, you will end up with this equation, which is this force is denoted by the centripetal force Fn equal to the mass of this particle, which is m, times its acceleration, which is this normal acceleration component An. The mass we already know as denoted by m, and then the acceleration we have derived in the previous step, which is v squared over r. So you end up with the equation for the centripetal force, which is saying Fn equal to the mass of this particle times the velocity squared divided by the radius of this circle. So that's the end of this presentation. So the main objective of this part of the presentation is to discuss the motion of a point mass which is going through a circular path. So then the equation we derived in this section will be used in the next video to explain the circular path motion of a rigid body. So after that, eventually we can come to a conclusion at the end of the third video, the scientific concept behind the pivot point in ship maneuvering. So here I am trying to build the basic foundation that you need or that you want to understand the ship pivot point, the concept of ship pivot point. So hopefully you have enjoyed this video, and so if you are still interested, please stick around. Thank you.